This lecture we're going to go over a little bit more in detail about soil water movement and what its effect is on soil moisture, plant availability, and so forth. Now remember that we talked about water movement in terms of saturated and unsaturated flow. In saturated flow, what's dominating here is just the sheer volume of water. This is the mass flow. So you get this big, when the soil is saturated, the whole bulk of soil moisture is flowing due to gravity. And that mostly takes place in macropores, okay? Now in unsaturated flow, this is where things tend to flow a little bit more slowly. And this is because of the capillarity, which are the tiny micropores, and the smaller pores in the soil can cause that suction. I think we talked about the matrix potential. Matrix potential is often categorized as unsaturated flow. And so when you think of the two, the big difference is that gravity is driving one of them, and which is the saturated flow, and then other forces such as matrix potential and pressure potential are kind of dictating the unsaturated flow. Now in all cases, water flows in response to energy gradients. I think I explained this last time, is that there's a gradient of moisture from the soil to the plant to the atmosphere. And so water is moving from a zone of higher potential to a zone of lower potential. Now saturated flow takes place because let's say the soil pores are completely filled, okay? And unsaturated flow, this is going to occur when the soil pores are filled with moisture but also with air. And so that only leaves the smaller pores to hold and transmit water. And then there's also a vapor movement, and this occurs as vapor pressure differs develop in dry soils. And so that's kind of a more minor form of movement, but it is one of the terms that we'll again, remember this graph here where we're showing how sand and clay soils differ in water content, and in terms of available water also they're different. Because the loss rate is so much different. You'll notice that the water content, as it goes up, the rate of loss goes up also very fast. Whereas clay, as the water content goes up, the loss rate, it kind of levels out here for a while and then increases. So again, all this water movement and water availability is highly dependent on soil texture. Again, what are the drivers? Gravity, matrix potential. Remember that matrix potential is the force that the soil surfaces and capillaries have on pulling water from higher instances of soil water potential to lower. And then we've also got removals. So what are the removals? They're evaporation. We could have some drainage that's like leaching, and we could have plant uptake. And then there's other activities too that can remove water. Now here's two terms that I want you to become very familiar with. They are transpiration and evapotranspiration. Okay, transpiration is what the plant pulls out of the soil and then evaporates out through its stomata. That is transpiration. Also in the soil, we just get plain old evaporation, and you know what that is. That's where you have a wet soil and dry air, and again, that gradient from wet soil to dry air is going to cause that evaporation. In agriculture, a lot of the time we talk about evapotranspiration. And what evapotranspiration is it's just a combination of transpiration, which is what the water that the plant uses, and evaporation, which is what is simply evaporated off the soil surface. So those two elements make up evapotranspiration. The reason it's important in agriculture is that we may be interested in evaporation and we may be interested in transpiration, but really when you're irrigating a field, you have to irrigate to meet both of those losses. And so we kind of condense them into evapotranspiration, and that's what we usually deal with in agriculture. Again, remember what capillarity is that it's the size of the pore. So we can get rise in water depending on the size of the pore. So here we're looking at a tube, but as the diameter of the tube narrows, you'll notice that that force of adhesion and cohesion can pull water up higher than if the diameter is larger. Again, this happens in the soil. So a soil with more micropores, you can imagine, has the potential to pull water up higher than a sandy soil. And I'm going to give you a couple of graphics here to kind of demonstrate that. What you're looking at here are two different soils. First we have a sandy loam and also a clay loam with quite a bit more clay. Both of these show different wetting fronts. Okay, you'll notice that this sandy loam, we've got a 15, 40 hour and 24 hour wetting front. And look at the shape of this. This wetting front, it does move out a little bit, but it mostly moves down. Now, in a clay loam soil, to get the same depth of wetting front, it took twice as long. However, you will notice that the wetting front goes laterally much more than the sandy loam. And why is that? The reason is because of that capillarity. There's a lot more capillary space in a clay loam soil than in a sandy loam. So right here we're dealing with mostly macropores, and over here we're dealing with a lot more micropores. And like I showed you with that tube on the previous slide, just imagine there's a lot more little tubey things sticking out here that are able to pull the water from the wetting front out. So generally speaking, there's three different fates of water on the soil surface. First of all, we can displace all the soil solids. The moisture can enter the soil, or it can run off the soil surface. Now, when the soil displaces all the solids on the surface, that's when we get kind of a sealing or a crusting look on the surface. I think you've probably all seen this before. It's fairly common when we go in and till ground and kind of beat up the ground and really destroy that soil structure. What happens is when the water hits that surface, it can seal it, and it can cause crusting. Now, once the water enters the soil, there's two things that go on. One is infiltration, and one is percolation. And then lastly, we can get runoff, and that can happen in the form of erosion, something I'm sure that you're all familiar with. Let's talk about infiltration and percolation a little bit more in depth. So once the water has infiltrated the soil, the downward movement of water is termed percolation. Okay, and percolation happens in both saturated and unsaturated flow, and it's related to the soil's hydraulic conductivity. So remember that hydraulic conductivity is the rate at which water moves in the soil. Okay, and remember that saturated and unsaturated flow are not the same. In the case of water that's infiltrated a really dry soil, you can observe how the water moves by the darkening of the soil, and a few key indicators that you can tell. And I think when we were doing our study of soil horizons and whatnot, you guys probably saw this. But what you're looking at here is a soil profile, and if you look along this dotted line, what you're looking at right here is the wetting front of this soil. And so what happens is water reaches the soil surface, it infiltrates, and then it percolates down the soil. But you can see that that rate of water flow is not even across this soil horizon. So, you know, maybe there's something here that's slowing up the flow of water. Maybe there's a sandy spot here that's making it go faster. There's a bunch of different factors that can change the rate at which water flows in the soil. However, but you can see in this case this wetting front, and it lends you some information as to how the water moves in the soil. So, just like everything in nature, there's a soil and water cycle, okay? We can either have irrigation or rain that act as inputs. We can have transpiration. That again is the water movement through the plant. We can have evaporation, and those are losses that we don't necessarily get back. There's runoff. And that can be in the form of erosion. And that can be recovered, you know, if some of our water runs off and we can collect it in a ditch and pump it back onto the field, that's great. And then we've also got deep percolation. Some of that also can be recollected. However, if it goes too deep into the soil profile, it and any nutrients that are associated with the water can leave with it. And so really in the soil, what we're trying to do is match our inputs with what our plant needs, and to try to maintain a balance of how much water the plant has available to it. Because if we have too much water there, like I said before, we can get nutrients moving. That's not acceptable. We can have erosion. We can have deep percolation and loss of water that way. So it's really kind of a balancing act. Okay, let's talk about infiltration and runoff with time. So what you're looking at here is on the y-axis we've got infiltration rate, and then we've got time after watering. So imagine that someone has a sandy loam soil and a clay loam soil right here, and they add water, okay? And you'll notice that initially the infiltration rate is very high, but over time it slows down. Same thing with this clay soil. Initially we have a fast infiltration rate, but after watering, that infiltration rate really goes down because of the clay in there. And the difference between these two, you'll notice that the sandy loam, even after it's kind of leveled off, and about the same time that the clay loam has leveled off, the infiltration rate is still faster than this clay loam soil. We'd expect that, right? We expect water to move faster through sandy soils than it does through clayey soils. And so if you think of this in terms of rainfall application, so let's say that we have right here we have an application rate, okay? Initially we have a fairly fast infiltration rate, but over time that infiltration rate drops down. Now if we're still applying water, because that infiltration rate is dropping, our rate of runoff, so this is water that can you put on the water and it can pond and then run off, the potential rate for that is increasing. So it's something that you have to keep in mind, is that soils do not take water, let's say you start out with a dry soil, it does not take water the same speed when it's dry as it does when it's wet. And that's what these two graphs are trying to show, is that initially we have a fairly fast infiltration rate, but over time it slows off. And because it slows off, then our potential for runoff, or this runoff rate, is increased. And again, this has to do with our soil texture. Now, looking at this graph, what we have is water content and depth. So when we add water, let's say that we put on a nice application of water, we might initially start out with some ponding up here. And then we've got a zone down here that's wet. And then this right here, our region here between wet and dry, this is called our wetting front. Okay, the wetting front is basically the contact zone between wet soil and dry soil. Now, this is early on an irrigation event. Now later, what happens is our water content starts to move down. Okay, so this line that you're looking at here was the early water content, and over time, as you'd expect, it moves down. And one of the things that happens is that our ponded water up here kind of dissipates, and it kind of evens itself out down the profile. So usually what we'll see is that towards the top, our soil moisture content's a little bit higher than down towards the bottom. So down where this color is changing here might be where we're starting to see some drop off in our soil water content. And so, like I said, there's a few different zones of soil water. Okay, we've got our dry surface. Maybe we can have some partially filled soil pores here with water, and then down here we can have a wet soil. And so, if our soil is left to dry, then over time, and again depending on soil texture, we can get some of this water that evaporates into the air from the subsurface. Okay, again, another short presentation, but I've got others coming, and I'll post them as soon as I've got them done.